Hello, this is Dr. Vaughn. We're going to look at question 1 for the Chapter 10, Part 1 homework for business stats. So this is a question, it's going to be involving what's called an independent samples t-test. So in this case, we have two groups, and we're looking at the mean of group 1 and the mean of group 2, and we're wondering if, based upon the evidence that we have, that we can conclude that the means of those two groups is the same. So this is the kind of test that we're doing. In this particular case, we need to be concerned about whether we assume that the variances and therefore the standard deviations of the two samples are actually the same or if they're different. So we're going to use Excel. We're also going to make reference to the PowerPoint slides from Pearson. You can access those through my stat lab. So we're going to start by looking at the mean number of calories for the cheesecake group and the mean number of calories for the organic fruit salad group, 799 and 1044. So I've started to type these over here. I just put, this is all text characters so far. I haven't done any computations. I'm going to insert a new row. We'll put up here, this is the cheesecake group. And over here, we're looking at the fruit salad. All right, so the sample 1 is the cheesecake group, and the sample 2 is the fruit salad. So mean number of calories that they estimated for the cheeseburger, 799 and 1044. All right, and then the study was based on a sample of 20 students in each group. So we'll have our sample sizes. 20 here and 20 over here. And let's see, the standard deviation of the number of calories was estimated to be 124 for the cheesecake group and 144 for the fruit salad group. So we'll put in our standard deviations. For the first group, that's 124, and for the second group, that's 144. And we have any other information? Okay, that's it for the preamble. Now we're going to state the null and alternative hypothesis if you want to determine whether the mean estimated number of calories is lower for the people who thought about the cheesecake first than for the people who thought about the organic fruit salad. So the keyword here is lower. We're going to be looking at a one-tailed test where we want the mean of group 1 to be lower in the alternative hypothesis than those who thought about the organic fruit salad. And so the alternative hypothesis is always the side that does not have the equal sign. The equal sign is on the null hypothesis side. We are doing a one-tailed test because it says lower. And so we can rule out C and D. And now I'm going to look at the alternative. Mu1 is less than mu2. And then the null hypothesis is the opposite side. I think it's A here. Fantastic. All right, now we're going to go on to part B. In the context of this study, what is the meaning of a type 1 error? Remember that a type 1 error is when you reject the null hypothesis and really you shouldn't have. So in other words, this is the, you found yourself to be in the tail, but that really was due to an exceptional sample. It wasn't due to a true observed difference of any kind. So one would conclude that the mean estimate is significantly lower when it's really not significantly lower. Again, I think that's part A here. Now a type 2 error. A type 2 error is when you fail to reject the null hypothesis. And in other words, you conclude that there really isn't any difference, or maybe thinking about cheesecake made the people estimate the calories even higher when we were only looking on the low side. So you fail to reject the null hypothesis when really you should have. So you conclude that the mean estimate is not significantly lower. That's not failing to reject the null hypothesis when it really is significantly lower. So I think that's D here. Okay, now we're going to go on. Assuming the population variances are not equal, we're going to use a 0.01 level of significance. Let's put that into our sheet over here. So our alpha, our level of significance, 0.01. And now we're going to find the test statistic, this t-stat. All right, so we'll go over to our slide really quick and we'll look at, here's the formula. This is on chapter 10, slide 9. This is the formula for the standard deviations are assumed to be equal. So we're going to do the pooled variance, which is this SP formula, and then we'll use SP in the denominator over here in order to pool the variance together in order to calculate this t-stat. So the first thing that I want to do in Excel is have it compute this pooled variance. So we'll jump right over to our Excel spreadsheet, and we'll compute down here the pooled variance. All right, so we're going to tab over, and we'll start with equals. Now we need to kind of just roadmap this formula. I hope that you guys are becoming a little bit better at this as the class goes along. So I need to take n1 minus 1. So numerator, I'm going to do a big parentheses for the numerator, and then a big parentheses for the denominator, and a dividing line in between. So in the numerator, I have open parentheses for the numerator, and then I'll have another open parentheses. I need to do n1, so our sample is n1 is b3, minus 1, close parentheses, now times, S1 is the standard deviation of sample 1. So we're going to do times this cell B4, that's the standard deviation quantity squared. All right, now we need to do plus, and then we'll do parentheses N2, which is also 20, or D3, minus 1, close parentheses, times, now we need to do standard deviation for the second sample, quantity squared, and that's the entire numerator. So now we're going to do divided by, and I'll do open parentheses for the denominator, and then we'll do n1, need a parentheses there, parentheses, n1 minus 1, close parentheses, plus parentheses, n2 minus 1, close parentheses for the n2 minus 1, and then close parentheses for the denominator, and then press enter. So this is our pooled variance SP squared. Now we're going to compute the t-stat. And following the formula again, we'll do equals, and the numerator for the open parentheses for the numerator, and then open parentheses. Now this is the difference between the sample means, so I'm going to do x1, which is b2, minus d2, close parentheses. Now minus mu1 minus mu2. Now in this particular example, we're assuming that the mu1 and mu2, the difference between them is 0 in the null hypothesis. So in other words, if there really is no difference. Now, in a lot of these cases where you're doing the independent samples t-test, this mu1 minus mu2 is going to be 0. The cases where it wouldn't be 0 is if you're actually testing a hypothesis that there's a known gap between the two groups. You know, that the population from which group A was drawn is a certain amount, and the population from which group B was drawn has a certain mean. And those two means of those two populations are expected to be different. In this case, we're actually expecting those populations to be the same, and we're just testing whether there's a difference actually between the observed samples or not that's significant. So this mu1 minus mu2 is actually 0. So the numerator is really just this b2 minus d2 in our case. And so I have a redundant pair of parentheses there, but I'd rather have redundancy than not have it there at all. Now in the denominator, I need square root, so that's SQRT, parentheses, and then I need to take this SP quantity squared. So SP was this, SP squared, I'm sorry, was this pooled variance, which is in B8. I don't need to square that, it's already SP squared. And now I'm going to do multiplied times parentheses 1 divided by N1 plus 1 divided by N2. And close parentheses for the 1 over N1 plus 1 over N2. Close parentheses for the square root. And that should be it. I don't really need a parentheses around the square root because that's the only thing that's in the denominator here. All right, so our t-stat is negative 5.76. 574. We'll hop back over to our homework, and it wants us to round it to 2 decimal places. So we'll round this to 2 decimal places. Negative 5.77. Let's see how we did. All right, fantastic. Now, now we're going to find the p-value. Now remember, the p-value is taking this observed statistic. We're doing only a one-tailed test, so we want to find the proportion that would fall below this particular observed statistic. So this p-value, in our case, is going to be equals, we're only doing a one-tailed t-distribution, and the degrees of freedom are going to be this, you know, t-stat has degrees of freedom n1 plus n2 minus 2. So we'll have to remember that when we go to do our inverse distribution. So t dot dist, and we're just doing the one-tailed, so I don't need to do that. The cutoff value that we're going to use is the t-stat from cell B9. Then the degrees of freedom is going to be this n1 plus n2 minus 2. So we'll do comma 20 plus 20 minus 2 and cumulative true. Close parentheses, and that should give us our p-value. Okay, again, this is in scientific notation, so times 10 to the negative 7th. When you round this to the third decimal place, it's going to be 0.000 rounded. It's not exactly 0, but it's darn close to 0. All right, so we'll round this to 3 decimal places and put 0.000. And finally, we're going to draw our conclusion. So the p-value is low. When the p-value is low, you reject the null hypothesis. So we reject the null hypothesis, which means that there is evidence that the mean number of estimated calories is lower and it's statistically significant. And there we go. We're done with question 1. This has been Dr. Vaughn, and we'll try to make another one. See you in a bit.